Recording in progress. Okay, welcome back. So in the last session, we have started discussion about the Gauss law. What is the Gauss law? Is a very simple thing. Yes. So the net electric flux is equal to total charge enclosed. That's all it is. Clear? So you need to find out only the charge which is inside. You need to discard the charge which is outside. This is the definition form. Net electric flux. This is a integral form. This one is a point form, or you can also call it as a differential form. All the different forms are conveying the same thing, but in a different mathematical operators. Q by epsilon, some books will say here, they'll represent it as a closed surface integral of E dot dA is equal to Q by epsilon, where D is equal to epsilon into E. Yesterday we have solved one problem. Now today I have asked you to do this one. How many of you are done with this one? What is the answer? What is the answer for this? No. Yes. Oh. Good. 150 nanocoulombs. Not root 3. Any more answers? Yes. Let us try to have some understanding of this one first. Okay. Observe, read the question carefully. Little bit visualization is required to deal with this one. Yes. If the line charge of density, how much? Rho L is equal to 15 nanocoulomb per meter. Fifteen nanocoulomb per meter exists at x is equal to 2 meters, comma, y is equal to 4 meters. For all z, that means parallel to the z. Calculate the net flux leaving the cube x comma y comma z ranging from -5 to +5. Let us draw the coordinate system here. If you visualize this one, it is a very simple question. Let us draw the coordinate system to understand this one properly. Here it is x-axis, here it is y-axis, here it is z-axis. What is x beta? X is 2. 1, 2. What is y? 1, 2, 3, 4. Let me make some box out of this. X is 1, 2. 1, 2. Y is 4. 1, 2, 3, 4. Let us make some box out of this one for the 3D visualization. So the infinite line charge is placed like this. Clear? Which is extending from minus infinite to plus infinite. And what is the charge on that one? 15 nanocoulomb per meter. Now this is enclosed with the cube of box whose side is ranging from -5 to +5 beta. Clear? Yes. So let me draw like this. Clear beta? So is that line is inside the box or outside the box? Yes, obviously it is inside the box. Let me draw this one properly. It is proper only. Its side is ranging from where? -5 to +5. So what is the side of this one? 10 meters. So is the line is infinite line is inside the box? Yes, it is inside the box. And what is the section of the line which is inside beta? 10 meters of line is inside. So you need to consider only the section which is inside. Why? Because what is the net flux beta? We know that net electric flux is equal to charge enclosed, charge which is inside the closed surface. Isn't it? Charge ENC. So what is the section? What kind of charge is this? Here it is a line charge, Royal nanocoulomb per meter. So what is the section of the charge? Net electric flux is equal to line charge is given. So what is the section of the charge beta? 15 nano into 10 meters of the line is inside the cube. So here it is net electric flux is equal to 150 nanocoulombs is the answer. Is it clear? Yes. Let us take one more question, beta. Is it okay? Fine. Let me take the one more question. I'm going to turn the page. If a line charge density Royal is equal to 50 nanocoulomb per meter exists at y is equal to sx in the z is equal to 0 plane. Calculate net flux leaving the cube x comma y comma z ranging from -5 to +5. Yes, what is answer beta? Come on, speak out. What is answer? So the infinite line charge is placed like a line crossing through the origin. Y is equal to x is a line passing through the origin. You need to multiply with what? One of your friend has answered. Very good, Kushal. Yes, yes. Yes, very good. Divyasri. Okay, see here, beta. Let me draw the coordinate system like this. Here x-axis, here y-axis. Where this infinite line charge is located, beta? This infinite line charge is located at x is equal to y. That means it is like a straight line passing through the origin. This is a line charge. And this is y is equal to x. This is on z is equal to 0 plane. So here is the thing. It is an infinite line charge. What is the charge on this one? Rho L nanocoulomb per meter. Now this is enclosed with the box, beta. Okay, box is like this. I'm drawing only the two-dimensional view. Actually, it is a box like this. Something like that box. Two-dimensional view is enough. So what is the this one? What is this range? It is ranging from -5 to +5. What is the length of this one, beta? 10 meters. Length of this one is also 10 meters. So what is the section of the line which is inside, beta? What is length of this one? Here it is 10√2. So the 10√2 section is inside the box. So what is the Gauss law? Net electric flux is equal to charge enclosed, ENC. So the net electric flux is equal to, how much is the charge? 15 nano into 10 into √2 beta. So here it is 150 √2 nanocoulombs is the answer. This much is the flux which is coming from the box. Is it okay? Fine. Let us have one more question. I'm going to turn the page here. Here is a question. This was one of your previous question. Let D is equal to, in the EC paper, D is equal to 2 rho square rho cap plus z cap nanocoulomb per meter square exists inside the cylindrical region enclosed by the surface. Rho is less than or equal to 1 meter. comma, z is equal to 0 and z is equal to 5 meters. Find total charge enclosed by the surface. See here, these questions, these type of questions were all noticed in the previous papers. The models. I'm not solving the exact gate question. Just I'm taking my own numericals and same models. So that when you solve the previous questions, you will feel them as a new questions. If I solve already in the classroom, there is nothing to solve for you in the previous papers, isn't it? The same model of questions are noticed. Okay. This is a question. This was asked in the EC paper for 2 marks. What should I do better? Let D is given. D is the electric flux density, isn't it? Exists inside the cylindrical region enclosed by the surface. Rho is less than or equal to 1, comma, z is equal to 0 and z is equal to 5 meters. Find the total charge enclosed by the surface. See here. What is the net electric flux? According to the Gauss law. What is the total charge enclosed according to the Gauss law? Q enclosed ENC is equal to net electric flux, which is equal to closed surface integral of d dot dA. Clear? Yes. But never perform closed surface integral. Go for a divergence theorem, which will make our life simple. What is the divergence theorem, beta? Divergence of d into dv beta. So I'll going to use this integral. Okay. So one more thing here. What is this differential volume dv? dv is equal to rho d rho d phi z cap. And what are the limits he has provided? The rho is less than or equal to 1 meter. Does it up to 0, infinite, minus infinite? No. The rho limits are only from 0 to 1. If he has not specified, you need to take it as a full limit, 0 to 2 pi. Z is from 0 to 5 meters. Clear? Yes. So find out the divergence beta. What is the divergence of D? 1 by rho into. In the cylindrical coordinate system, what is the divergence formula? 1 by rho into d rho. I have given everything. Now it's a time. Now it's your time to recall the things. We have spent very qualitative time on the vector calculus and coordinate system. Now you need to make a use of all the formulas here. Dou by dou phi of d phi plus dou by dou z of rho into dz beta. There is no phi component here. There is only rho component and z component. So this part is 0. So which is equal to one by rho into dou by dou rho into d rho. What is d rho? 2 rho square plus dou by dou z into rho into z beta. So which is 1 by rho into 2 rho cube can be written as 2 into 3 into rho square plus rho. So which is 6 rho plus 1. And one more thing, always you need to cross check the units. What are the units here? Its units are nanocoulomb per meter square multiplied with the meter square. So you will going to get this one, nanocoulombs. Anyhow, you have got a divergence of d beta. I'll going to turn the page here. This was a 2 marks question. So the divergence of d is also equal to rho v, which is equal to 1 plus 6 rho beta. Units are nanocoulomb per meter cube. So to get charge enclosed, you need to perform what is called a volume integral. 1 plus 6 rho into rho d rho d phi dz. Clear beta? Yes. Okay. So what is the charge E and C beta? Separate out the variables. Can I write down directly? 6 rho square plus rho into d rho. Here it is d phi. Here it is dz. Here it is 6 rho cube by 3 plus rho square by 2. The rho limits are from 0 to 1. Here it is phi. Limits are from 0 to 2 phi. Here it is z. Limits are from 0 to phi. Upper limit minus lower limit beta. Here it is 2. So 2 1 cube plus 1 square by 2 into 2 pi into 5. So here it is 5 by 2 into 2 pi into 5, which is 25 into pi. Charge enclosed is equal to 25 pi nanocoulombs answer. Clear beta? Yes. So these are one model of questions expected. Finding the net flux or finding the charge enclosed. The other model of questions are finding the electric field using the Gauss law. How can you find out the electric field using the Gauss law? Let us have some theory. Please be focused. Before that, as I said earlier, there is a relation here. Note. There is a relation between D and E. I'll justify this one later. What is this D is? Electric flux density. It is talking about number of lines. and its units are coulomb per meter square. This is electric field intensity. What it is? Electric field intensity. It is talking about the magnitude. Its units are volt per meter. Clear, beta? Okay, fine. So let us focus on the actual thing. I want to find out the electric field using the Gauss law. How can you do that? Finding electric field. Finding electric field using Gauss law. Little bit visualization is required here. Now let us see how you need to proceed. Please be focused. Consider the Gauss law, beta. Consider closed surface integral of dDA is equal to charge ENC means charge enclosed. Here D is equal to epsilon into E. Okay. And there is I'll consider the medium to be homogeneous. What is the meaning of homogeneous? Wherever you see, the medium will going to look same. Yes. So for homogeneous medium, epsilon is constant. You can substitute there. Epsilon into E dot dA, which is equal to charge ENC. From here, first let me write down the theory. So you're going to get closed surface integral of E dot dA is equal to charge ENC by epsilon. Now I'll choose. So from here, I want to get the electric field expression. How can I get the electric field expression? So to get the electric field expression, what I'll do, I'll appropriately choose this Gaussian surface. The closed surface is called Gaussian surface. Okay. So the entire idea exists in choosing the appropriate Gaussian surface. What is this one? This is a Gaussian surface. How should I choose the Gaussian surface? Step number 1. There are 2-step procedure here. Choose Gaussian surface such that this dot product E dot dA either should become a simple product or 0, such that E dot dA what is this E dot dA? E dot dA into n cap, isn't it? Area direction is a normal direction. Either it should become a simple product or 0. That means it should become E into dA. When does that become E into dA? And one more thing here. Just a minute. Here it is. E dot dA or E dot dA into n cap or E dot dA into cos theta. All these are same. So you need to choose the Gaussian surface such that this E dot dA either should become a simple product. E into dA. When does this happen? When this angle is equal to 0. Or it should become 0. When does this happen? When angle is equal to 90 degrees. So this dot product should become a simple product or 0. That means this electric field direction and the normal direction either should be the same or perpendicular. That is how you need to choose the Gaussian surface. Clear? Step number 2, beta. If E dot dA is equal to EDA, if the dot product becomes a simple product, then E must be constant on the Gaussian surface. E must be constant on the Gaussian surface. So if E dot dA is equal to, if the dot product becomes a simple product, then E must be constant on the Gaussian surface. So if the E is constant on the Gaussian surface, what has become here? The dot product has become a simple product, E into dA. Clear? So on this Gaussian surface, this E is constant. If that E is constant, what you can do? You can bring that one outside. So if you can bring the E outside, as the E is constant on the Gaussian surface, as you can bring the E outside, obviously what it is beta? You will get an expression for the electric field. Okay. So this two-step procedure, I will so nicely explain with the help of one example, known example, so that you'll appreciate this one, what actually it means. Okay. First, let us see the known things so that we'll understand this procedure. After that, we'll go to the unknown things. Clear? Let us have some examples beta. I'll go to turn the page. Example number 1. Let us take it for the point charge. What is the electric field due to the point charge? E is equal to Q by 4 pi epsilon R square into R cap. Let us consider the point charge here, Q. If the Q is the point charge, what is the electric field? It is radially outwards. Okay. So the electric field is radially outwards, ER, 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 ER and ER. So what is the appropriate Gaussian surface for this one? How you need to choose the Gaussian surface, beta? I want answers from your side. I need to choose the Gaussian surface such that the Gaussian surface area, that means normal direction, and the electric field either should be the same or should be the perpendicular. Yes, any answers? Come on, very good, very good. Let us go by the trial and error method. Let us consider the box like this, a cylinder like this. Is it a Gaussian surface for the point charge? Suppose if you consider like this, what is the normal for this one, beta? Normal here is like this. 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 Normal here is like this because it is a closed surface. So normal direction and electric field directions are not same, not even perpendicular. They are making some angle. Here also same story. Normal direction and electric field directions are making some angle other than 0 and other than 90. So the cylinder is not a best suited Gaussian surface for point charge. Now let us consider the box, beta. Is it a best suited? Outside, 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 outside. They are making some angle here. So this box is also not a best suited Gaussian surface for the point charge. Then obviously, what is the best suited Gaussian surface for this one? Sphere. How can I convince that is a sphere? By putting a dots here. And what is the radius of the sphere is R. And what is the normal direction for this one? It is a sphere, closed surface. Normal direction is outwards. Array. Electric field direction and normal directions are same. Yes or not? So apply that Gaussian surface, beta. What is the Gaussian surface is? Gauss law is closed surface integral of E dot dA is equal to charge ENC divided by epsilon. I am using the color this one. That means I am applying that one over this. That is the meaning of that. So what is the charge inside this one? Is Q divided by epsilon. Clear? And the electric field direction and normal directions are same over that Gaussian surface. So what happens here? Dot product will become simple product. ER into dA, which is equal to Q by epsilon. Now this electric field is constant over. It is also satisfying the second condition. If E dot dA is equal to EdA, then E must be constant on the Gaussian surface. That means the electric field strength here to here, here to here, here to here, here to here, here to here will be same. Why? Because it is a sphere, the radius is same, electric field strength is same. So on that Gaussian surface, the electric field is constant. So you can bring that one outside. Here it is Q by epsilon. So what this is indicating, beta? It is a surface area. Surface area of the sphere. What it is? 4 pi r square, which is equal to Q by epsilon. So the ER is equal to Q by 4 pi epsilon r square. So the electric field is equal to Q by 4 pi epsilon r square into r cap beta. Clear? So this is the electric field expression we have got, which we already know from the Coulomb's law, isn't it? Is it matching with this one? Yes. That is the story. Let us take one more example for further clarification. Let me turn the page better. Let us consider the infinite line charge. Example number 2. I am taking the known examples for your visualization so that you can deal with the unknown values, unknown examples. Infinite line beta. Infinite line charge. Infinite uniform line charge, you can say. What is the electric field due to the infinite line charge beta? E is equal to rho L by 2 pi epsilon rho into rho cap. Yes, observe here beta. Now let us consider the infinite line charge. Which is extending from minus infinite to plus infinite. Okay, fine. So what we know? We know that due to the infinite line charge, electric field is radially outwards. Here it is zero. So what is the charge on this one? It is a line charge, rho L coulomb per meter. Now, please help me. What is the best suited Gaussian surface for this one? Come on, I want answers from your side. What is the best suited Gaussian surface for this one? Ah, cylinder. Very good. Yes, I'll directly take the cylinder. Yes. So this is having a length. This is having a radius rho. Let us say. And this is having a height h. Clear? And what about this one for the cylinder? The normal direction is outwards beta. It is n cap. It is n cap for the downward, for the top bottom surface, it is n cap. Here it is n cap. For the side surface, here it is n cap. 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 So for the sides, electric field direction and the normal direction, that means area directions are same. For the top and bottom, it is perpendicular. Okay. So if it is it should be either along the direction or perpendicular, but it should not be between them. Okay. Yes. It is satisfying the first one. Now let us consider the Gaussian, this Gauss law beta. What is our Gauss law is? Closed surface integral of E dot dA is equal to charge enclosed by epsilon. I am applying this one over this Gaussian surface. Clear? So which is equal to rho L into H divided by epsilon beta. What is the charge inside that? Rho L into H. Now I am going to split that integral. I am applying this one over the cylinder. Cylinder will have three surfaces, top, bottom, and then sides. I am going to split that one into the three parts beta. Here it is the top E dot dA, bottom E dot dA plus sides E dot dA, which is equal to rho L into H by epsilon. Okay, beta. For the top and bottom, for the top, normal is like this, electric field is like this. That means for the top and bottom, area direction is like this, electric field direction is like this. So they are making 90 degrees. So the top integral and bottom integrals will go 0. So the top integral will go 0 and bottom integral will go 0. But what happens for the sides beta? Electric field direction and normal directions are same. Clear? So what happens to the sides integral is it will become simple dot product. E rho into dA, rho L into H by epsilon beta. And you are maintained, this is a circle like thing. On that electric field strength from here to here, here to here, here to here, here to here will be same on the surface of the cylinder. So the electric field is constant on that. So you can bring this one outside. E rho is equal to surface integral of sides into dA, which is equal to rho L into H by epsilon. This is indicating the sides area beta. What is the side area? 2 pi rho into H beta, isn't it? So here it is. E rho is equal to 2 pi rho into H, which is equal to rho L into H by epsilon. So just cancel out H on both sides. So what you're going to get? E rho is equal to 2 pi rho is equal to rho L into epsilon. E rho is equal to rho L by 2 pi epsilon into rho. So if you write in terms of vector, E vector is equal to rho L by 2 pi epsilon rho into rho cap. Array, see here. The same thing you have got. Yes or not? Very interesting. Okay, fine. So these are the known exam. We know the results, isn't it? Now let us take something new examples here. Those examples will going to help us in solving the varieties of questions. Okay, beta, I'm going to turn the page here. Example number 3, beta. perfect solid conductor. Perfect solid metal block or otherwise. Something like a block which is filled right from inside to outside, which is not hollow. Something like a metal rod, which is filled right from inside to outside. Okay. Now observe here, beta. You should know some mechanism here. Let us take at some time t is equal to 0. There is a conductor. Solid conductor, something like a metal rod, which is filled right from inside to outside. Okay. So what I'll do here, I'll charge this one. I'll place the charges on that one. I'll place the charges inside that one. How do you charge something? By applying some friction. By connecting it to the potential. We'll come to that potential concept later anyhow. So by some means I've charged this one. I'm showing positive charges. It could be negative charge also. Or combination of positive and negative also. So I'm placing the charges on the conductor, inside the conductor. So what happens? Within no time, charges will repel each other, isn't it? Charges are free inside the perfect conductor. They can move wherever they want. So at the room temperature, they'll repel each other and they'll come and sit on the surface of the conductor. Isn't it? Yes. So within no time, just after this, T is equal to 0 plus. Within no time, so what happens? Charges will come and sit on the surface of the conductor. Remember, it is a block. It is not a surface. It is a metal block. So the charges will come and sit on the surface of the conductor. So the charges are spread over the conductor, isn't it? So how these charges can be characterized? These charges can be characterized as a surface charges. Generally, this is popularly known as a skin effect in your electrical engineering terminology. So the concentration of charges happens only on the surface of the conductor. So the charges will repel each other and they'll come and sit on the surface of the conductor. Okay. So how these are characterized, beta? These are characterized as rho s coulomb per meter square. Now I want to investigate the presence of electric field inside the conductor and outside the conductor. So same story, apply the Gauss law here. I'll apply the Gaussian surface here, just below this charge distribution. If I consider my Gaussian surface just below this one, what happens, beta? Is there any charge enclosed? No. So if the charge enclosed is 0, net flux is 0, electric field is 0. So here, electric field is unconditionally 0 inside the perfect conductor. Just forget about the physics, what is happening behind that. If you talk in terms of physics, what actually happening is the force here will balance, force here will balance. So the net electric field is 0. So inside the perfect conductor, the net electric field is 0. So can electric field exist? Because charge enclosed is 0, net flux is 0, flux density is 0, electric field is 0. Can the electric field exist on the conductor? Let us consider the Gaussian surface better. Now let us consider a outside the closed surface. Is there any charge enclosed? Yes, there is a charge enclosed. There is charge enclosed. There is charge enclosed here. If I consider the Gaussian surface outside, charge is there on the surface of the conductor. As a charge enclosed is there, so the electric field is not equal to 0. What is this yellow color is indicating? Is a Gaussian surface. So inside the perfect conductor, the net electric field is 0. On the surface conductor, there is an electric field. Then here my question is, how the electric field can exist on the conductor, tangentially or normally? See, one of your friend is asking, is it uniformly distributed charge? That depends on the surface beta. At the corners, the more charge distribution may happen. At the flattened region, the less charge distribution happen. That depends on the nature of the surface. Okay, come back to our question here. I'll repeat again. Inside the perfect conductor, the net electric field is 0. On the surface of the conductor, electric field can exist. My question here is, in which form, in which direction it can exist? I'll repeat my question, in which direction it will exist. Can it exist tangentially or normally? That means, can it exist like this or like this? It cannot exist tangentially beta. Let us say the electric field on the conductor is existing tangentially. What happens? That electric field again exerts the force on the charge. Okay. So because of that, charge start moving. If the charge start moving, current flow happens. Listen carefully. What I'm saying, if I assume that the electric field is existing tangentially on the conductor, so what does that electric field will do? Electric field will again exert the force on the charge. Charge start moving, current flow happens. But that is not the true. If you keep my conductor like this, conductor is creating its own electric field that is exerting the force on charge. Charge is moving, current flow is happening. No, that is not the case. For the current flow to happen, there must be externally supplied. External supply is required. So what I mean to say here is, electric field can't exist tangentially. So how the electric field can exist on the conductor? Normally. So how the electric field can exist on the conductor? Normally. Clear, beta? Yes, normally, not tangentially. So I'll repeat one more time what we have done here. So inside the perfect conductor, As soon as you place the charges inside the conductor, they are free. They can move wherever they like. So they'll repel each other and they'll come and sit on the surface of the conductor. Perfect conductor. So the no charge can exist inside the perfect conductor. Okay. So if I consider my Gaussian surface, the charge enclosed is zero, net flux is zero, electric field is zero. So inside the perfect conductor, the net electric field is zero. On the surface of the conductor, yes, there is a charge enclosed. So the electric field is not equal to zero. And how does the electric field can exist? Only normally, if it is a perfect conductor. Clear? So let me write down the points here, very important points. Later also we'll go in, these points will going to help us. So what is the point beta here? Inside the perfect conductor, charges will repel each other and tries to reside on surface of it, which is characterized by surface charge. Rho s coulomb per meter square. That is the first point. What is the second point? Inside the perfect conductor, the net electric field is zero everywhere. Inside the perfect conductor, the net electric field is zero everywhere. Electric field on the perfect conductor is non-zero and it exists in the normal direction. Electric field on the surface of conductor is non-zero and exists in normal direction. These are very important points. Later also we'll make a use of these points. These points anyhow, this will going to help you in the electrical engineering also. So this is example number 3. Now let us go to the example number 4. Very interesting example. Hollow closed conductor. Hollow closed conductor. Hollow closed conductor. It is something closed one, but inside it is hollow. Okay. Now observe here better. I'll draw the cross-sectional view. What happens? It is a hollow metal. It is a thickness. On this one, there is some charge. It is a hollow metal one, hollow closed one. How can I convince that is a closed one? By putting a dots here. So what happens to the electric field inside this one and outside this one? Come on, speak out. Hollow metal. It is a closed one. See here, it is something like this. If you consider this bottle as a metal one, inside this one, there is a hollow. So what is the inside electric field? What is the electric field outside? What happens to the electric field inside? First answer that. Inside it is 0. Yes. Same story. Let us consider the Gaussian surface here. Just below this one. Okay. Is there any charge enclosed? No. So what about electric field? Electric field is 0. On this one, electric field is not equal to 0 because it is enclosing the charge. You can see this one number. There are number of applications of this one. Take some stainless steel lunchbox. Stainless steel lunchbox. What you will find in your kitchen. Stainless steel lunchbox or bowl. Keep your cell phone inside that. Keep your cell phone inside that one and close it. Make sure that there should not be any air gap and call it from the other cell. You will get it as a no signal. Because it is a closed one. Inside that one, field is 0. Actually, EM phenomena will be there. High frequency signals will be there. Anyhow, electric field 0, that will make the magnetic field also to become 0. So there won't be any signal inside that. Yes. Generally, this is technically called shielding. What it is? This is called shielding beta. It is providing the shielding. So the no electric field is there inside that one. You can check this one. Or even when you go, while you are going in a lift, you can check out to your cell phone signal. Of course, signal will be there, but it is a poor signal. Especially when you are having a lift which is having a doors like this instead of the bars. So anyhow, there will be a gap for the air circulation. It is not a perfect closed one, but you can check out the cell phone signal, poor cell phone signals. Yes, you can check out this one. Keep your cell phone. If your smartphone cannot fix inside the stainless steel lunchbox, use your, if at all, if there is a small phone, geophone, place a geophone inside the closed that stainless steel lunchbox, close that one tightly without air gap and call it from the other cell. You will get it as a no signal. Okay, fine. So hollow closed conducting surface, the electric field inside the hollow conducting closed surface is 0. So what is this one? The electric field. Very interesting. Electric field inside hollow conducting closed surface is 0. Is always 0. Okay. Have you seen Vishwarupam movie? Kamal Hassan. Vishwarupam part 1 and part 2. There are 2 parts. In the part 1, In the climax, Kamal Hassan will keep bomb inside the micro oven. How many of you have remembered? The climax is something like this. Let me explain. There is a terrorist will deploy some bomb and they want to operate that one through the cell phone, other cell phone. They'll place one cell phone inside that in the bomb. And as soon as they call it from the other cell, so it will ignite and the blast takes place. That is the how the climax is. So somehow the Kamala Hassan finds the bomb and he want to defuse that one. But he could not able to do. So what he will do, he'll going to place that, he will place that bomb inside the microwave oven. What is the microwave oven? It is a closed one. It is a closed conducting surface, isn't it? That means he has provided some shielding. Even though the terrorists want to operate that, they cannot, signal cannot. That means that is under the shielding. So the signal cannot reach. So that is how the climax is. Okay, anyhow. Let us take one more example, beta. Example number 5. It is something different example. I'll going to place the charge inside the sphere. Listen carefully. Here is a sphere. There is some other mechanism is involved here. There is a sphere here. This is the thickness of the sphere. There is a charge I am placing here inside this one. It is not hollow. Inside the sphere, I am placing the charge. This is the thickness of the sphere. So what happens, beta, here? Come on, speak out. What is the electric field inside this one? See, the Faraday case is the same thing. Suppose if you have a case like a thing, previous question, previous example, it need not be perfect conducting closed surface. The case like thing you have, case means what? It is something like this. The bird's case. The bird's case, what you have. Even if you place your cell phone inside that also, there won't be any perfect reception of the signal. It need not be a perfect conducting closed for the radio signals especially. The case-like structure will also provide the shielding. This is called Faraday case. Why? Because why it is not called Gauss case? Because Faraday, what is the motivation for the Gauss law? It is a Faraday's law, isn't it? Faraday's experimental law. That is the reason why that is called a Faraday case. Case, pinjar in Hindi. Panjaram in Telugu. Okay, whatever it may be. Yes, please focus on this one better. Example number 5. I am placing the charge. There is a hollow sphere. Inside that one, I am placing the charge at the center or anywhere. So I want to find out the electric field. Same story, beta. I'll consider Gaussian surface here. If I consider Gaussian surface, is there any charge enclosed? Yes. So what about the electric field? Electric field is not equal to 0. It is not a hollow sphere. Charge is there inside the sphere. Okay, next point. Is there any electric field in the thickness of the sphere? I'll repeat one more time. Is there any electric field in the thickness of the sphere? No. Thickness of the sphere is a conductor. Inside the thickness of the sphere, electric field should go zero. But if I consider my Gaussian surface here, in the thickness of the sphere, what is charge enclosed, beta? Charge enclosed is Q. If the charge enclosed is not equal to zero, then electric field also should not equal to zero. I'll repeat one more time what I'm saying. What I want to check the electric field in the thickness. Undoubtedly, thickness is a conductor. Inside the conductor, electric field must be zero. But if I apply the Gauss law here in the thickness, if I consider my Gauss law, Gaussian surface in the thickness, it is enclosing the charge Q. If it is enclosing the charge Q, that means inside the thickness, electric field must not be equal to zero. That is again is the basic principle. So what happens? Conductor will nicely adjust the charges, will going to nicely induce the charges. What the conductor will do? Conductor will going to induce the negative charges here on the inner surface. How much is the charge it will going to induce? Minus charge. On the counterpart for that, plus Q charges is induced on the outer one. Now apply the Gaussian surface here. If I apply the Gaussian surface, what is the electric field, beta? What is the charge enclosed by this one? The charge enclosed by this one is Q charge and minus Q charge. So how much is that? Q charge minus Q is a zero. So the electric field in the thickness is zero. Unconditionally, it must be zero, beta. Clear? Yes. Now observe here. So then what about the electric field here outside? Charge enclosed is plus Q minus Q plus Q. So how much is the charge? Effectively plus Q. So the electric field here is not equal to zero. So that is the story. Clear? Yes. So the too many things are involved here. Inside the car also, there is no proper signal. That is the reason why you are having some small antenna. Car is not a perfectly closed one. Windows are there, which are of dielectric. Just to create the interest, I have given some examples here. Don't think much about that. That is, there are all high frequency models. Communication systems, they are all. Our frequency is limited 50 hertz. Okay. Speed and all those things is a different issue. It is altogether modulation techniques are involved. That entire thing is the communication. Just to create some interest on the shielding, I have given those examples. And you are asking, some of your friends are asking that doubts from that Vishwarupa movie. Okay, jokes apart, we'll go to the question beta here. I'll going to turn the page. So based on these examples, why I have given like this, we can draw, I can explain number of examples, but these examples will give the idea, and with these examples are important in that will give the idea in solving the questions. Clear? Now let us have a questions here, which are very interesting. If you can understand, if you have understood these these 5 examples, you can handle questions easily. Clear? Let us have a questions beta. Think about this one properly. For a uniformly charged sphere of radius r and charge density rho s coulomb per meter square. The ratio of magnitude of electric field at distance r by 2 and 2r from the center, that is E at r is equal to r by 2 divided by E at r is equal to 2r is, yes. What is the answer? Come on, answer. Need answers from your side. Yes, very good. Yes. 0 is the answer for this one. See here. Solution. Better see here. For a uniformly charged sphere of radius r, what kind of sphere he has not mentioned. Whether it is a conducting sphere or hollow sphere, that is not mentioned. For uniformly charged sphere of radius, how much? R. Charge density, how much? There is a sphere here. Okay. And this is a sphere is having a radius r beta. Charge is here. Let me draw the figure there. Okay. Whatever. It is characterized by the surface charge rho s. Units are coulomb per meter square. It is a sphere. Charge is there. So inside that one, what happens? The electric field is 0 everywhere. Yes. So the electric field is 0 everywhere. Electric field as outside is not equal to 0. Clear? So the numerator is 0 here. Denominator is not equal to 0. Yes. What is this one beta? E at r by 2. E at r is equal to 2r. So the numerator is 0. Denominator is not equal to 0. Which is equal to 0 is the answer. Okay. Most of your friends are asking me to repeat this example number 5. I'll repeat. See here, there is a sphere here with a thickness. There is a charge here. So the electric field here is not equal to 0. Clear? Why? Because if I consider the Gaussian surface. But if I consider the Gaussian surface in the thickness, charge enclosed is Q. But inside, if the charge enclosed is Q, the electric field should not be equal to 0. So to balance that one, this sphere will going to induce the minus q here and plus q here. So now what is the charge enclosed by this one? Plus q minus q. Net charge is 0. So as the net charge is 0 inside the thickness, that means inside the conductor of the sphere, the electric field is 0. So here charge enclosed is plus q minus q plus q. So the electric field is not equal to 0. That is the story. Okay. Let us take one more question, beta. I'll going to turn the page. Here is a question. Calculate the field at E is equal to R by 2, comma, E at 2R due to the volume charge as sphere of R radius and rho v coulomb per meter cube charge density. Options are given. Option A, rho v r divided by 6 epsilon naught, rho v r divided by 12 epsilon naught. Option B, rho v r divided by 12 epsilon naught, rho v r divided by 6 epsilon naught. Option C, option D, rho v r divided by 12 epsilon naught, rho v r divided by 12 epsilon naught. Here it is, rho v r divided by 6 epsilon naught, rho v r divided by 6 epsilon naught. Yes, beta, what is the answer? Yes? Any answers from your side? Let me go back. In this question, is just said a charged sphere. Okay. Yes, clear. If it is a hollow or it is a solid, doesn't matter. Charge will go and come and sit on the surface. In the hollow sphere and in the solid sphere, the electric field is 0. Yes, that is the reason why we have considered electric field at R by 2 is 0. What about this one, beta? Come on, speak out. I want answers from your side. Yeah. Yes, good. Let us see. Calculate the field at R by 2 and 2R due to the volume charge as a sphere of R radius and charge density rho v. So the volume charge is distributed like a sphere, beta. Okay, here is the case. Charge is distributed like a sphere like this. And what is the radius of this one? Radius of this one is rho v. And what is the charge on this one? Here it is rho v coulomb per meter cube. Is asking at r by 2 and 2r. Let us try to find out at r by 2 beta. At r is equal to r by 2, or simply r by 2. So at r by 2, I'll consider the electric field. I'll consider the Gaussian surface. My interest is at r by 2 beta. Here it is r by 2. This is a Gaussian surface. So what is my Gauss law is? Here it is. Closed surface integral of E dot dA is equal to charge enclosed by epsilon. I am applying over that Gaussian surface. Okay. So what is the charge inside this one? What is the charge inside that Gaussian surface? It is a volume into volume charge. What is the volume of that? 4 by 3 pi r cube. What is r beta? R by 2 cube into rho v divided by epsilon. Is that clear? Now you can bring this dot product will become a simple product. ER into dA. It is 4 pi r cube divided by 12 epsilon naught. He has considered free space into rho v. You can bring that ER outside beta. Here it is 4 pi r cube into rho v divided by 12 epsilon naught. Here it is surface area. Surface area is this one. Yes, what is the surface area of that one? 4 pi r square. R place r by 2 square, which is equal to 4 pi r cube into rho v divided by 12 epsilon naught. Clear? Yes. Something is missing here. Here there is one more 2. Okay, let me turn the page here. So what you're going to get? I'm going to turn the page. So the ER is equal to rho v into R divided by 6 epsilon naught. R simply you can write electric field at what beta? R by 2 is equal to rho v into R divided by 6 epsilon naught. Clear beta? Yes. Can you decide from the options? Rho v into R by 6 epsilon naught. The answer will be from A and C. Clear? Yes. So that is the thing. Now let me turn the page here. You need to find out at one more point also. Which point is that? 2R point. Let me do that one also. I'll draw one more time for figure. You no need to write in the exam. You no need to draw. But for my explanation purpose, to maintain the clarity in explanation, I'll consider one more diagram. Here is a sphere. Charge is distributed like a sphere beta. This is having a radius how much? This is having a radius of r. And what is the charge on this one? Volume charge rho v, units are coulomb per meter cube. Now I'll consider a sphere Gaussian surface. At what distance beta? At 2r. Gaussian surface 2r. Clear beta? Now apply the Gauss law. So what is the Gauss law? Closed surface integral of E dot dA is equal to charge ENC beta. Charge enclosed by epsilon. So what is the charge inside that one beta? Speak out. Charge is only up to here. Charge is not up to here. Charge is only up to here, up to the radius of r. You must be careful here. So here it is rho v. What is the volume charge? Rho v into 4 by 3 pi r cube divided by epsilon naught. That is the story. So after performing the dot product, what happens? Here it will become ER into dA, which is equal to 4 pi into r cube into rho v divided by 3 epsilon naught. You can bring this ER outside beta. Four pi r cube into rho v divided by 3 epsilon naught. That one is, this is a surface area beta. What is the surface area? The surface area is here. This area. What is the radius? You should consider. You should consider the 2r. Clear? Yes. So here it is. ER is equal to 4 pi 2r whole square, which is equal to 4 pi r cube rho v by 3 epsilon naught. So the ER will become rho v into r divided by 12 epsilon naught. So this is the electric field at 2r. 2r is equal to rho v into r divided by 12 epsilon naught. So what is the answer beta? Let me go back. Option A is the answer. Clear? Let us take one more question. I'm going to turn the page. Okay. Yeah. Here is a question. This was asked in the electrical paper for 2 marks. A solid sphere made of insulating material has a radius r and has a total charge Q distributed uniformly in its volume. What is the magnitude of electric field intensity? What is the magnitude of electric field intensity E at distance R, where R is from in between 0 to R, inside the sphere? Options are given. 1 by 4 pi epsilon naught Q into R divided by R cube. Option B, 3 by 4 pi epsilon naught Q into R by R cube. Option C, Q divided by 4 pi epsilon naught R. Option D, 1 by 4 pi epsilon naught Q into R by R cube. Don't get confused with the small r and capital R. That is where you'll go wrong. Yes, what is the answer, beta? Yes, what is the answer? Solid sphere made up of insulating material has a radius R, has a total charge Q, distributed uniformly in its volume. Charge is distributed uniformly in the volume means it is a volume charge. What is the magnitude of the electric field intensity E at a distance R inside the sphere is? Okay. See here, there is an insulating material. Okay. Clear, beta? And it is a sphere, beta, insulating sphere. And the total charge Q is spread over this one. Total charge is spread over this one. What is the radius of this one? Radius of this one is R. As the total charge Q is spread over this one in the volume, so the volume charge will be constant, isn't it? It is uniform. So the rho V is equal to Q by 4 by 3 pi R cube, Coulomb per meter cube. Now you want a electric field inside this one, beta, at certain radius of R. I have considered the Gaussian surface. Now, that's all it is. You can proceed. So what is my Gaussian surface? The Gauss law is saying closed surface integral of E dot dA is equal to charge ENC divided by epsilon naught, which is equal to what is the charge inside that one beta? Volume charge into 4 by 3 pi. That means you need to consider the charge inside this one. 4 by 3 pi r cube divided by epsilon naught. So here it is. ER into dA, same story. What is that rho v beta? 4 by 3 pi. Sorry. What is it rho v? Q by 4 by 3 pi r cube into 4 by 3 pi r cube divided by epsilon naught. So here it is ER. Which is Q into R cube by R cube into epsilon naught. What is this is beta? This is a surface area. Let me go back. Surface area up to R you need to take. Okay. So here it is. So here it is. ER is equal to Q into R divided by 4 pi epsilon naught into R cube. That is the thing. So the option A is the answer beta. Clear? Yes. So like this, questions are expected. Clear? So this is all about the Gauss law. We have spent very rigorously. And conclusions we have got are very important. Let us take one more question. This was one of your previous question. Given that the electric flux density D is equal to Z rho cos square phi Z cap coulomb per meter square. The charge density at point 1 comma pi by 4 comma 3 is see here. If he has nothing specified, you need to take the epsilon is equal to epsilon naught. That's all it is. Yes. He's asking the charge density. That means if the electric flux density is given, what charge density you can find out? Volume charge density. Do this one. What is answer? Very good. 0.5. Yes or not beta? Substitution kind of question. What is charge density? Rho V is equal to divergence of D, which is equal to 1 by rho into dou by dou rho into d rho plus dou by dou phi into d phi plus dou by dou z into rho into dz. So there is only z component here. Clear, beta? So these two components are 0. So this will become 1 by rho into dou by dou z into rho into z into rho into cos square phi. So here it is rho square by rho into cos square phi. So the rho v is equal to rho into cos square phi. Substitute at a point rho comma phi comma z 1 comma pi by 4 comma 3. So here it is 1 into cos square pi by 4 1 by root 2. Is the answer. Okay. Now let us go to the new concept here. I'm going to turn the page. Okay. Now let us we're going to see what is called a potential concept. Work done in order to move a charge. Work done in order to move charge. Or simply it is called electrostatic potential. It is represented with the symbol V. It is represented with the symbol V. Okay. Now let us start with the definition of work. Interpretation of work. How do you define the work, beta? What is the formula for the work? You have been learning this one from your childhood. Childhood in the sense in your physics. What is the formula for the work? Force into displacement, isn't it? Then how do you interpret the work? How do you interpret the work? Suppose if I am holding like this, am I doing any work? If I am holding this object, am I doing any work? No. According to physics, the work done is 0. According to physics, work done is 0. Of course, my body is burning some fuel. I am spending some calories to hold this one. But according to the physics, work done is 0. Suppose if I am moving like this, am I doing any work? Yes, I am doing work. Isn't it? For example, weightlifter. While he is lifting the weight, he is doing work. But when he reaches top, if he is holding like this, it will create lot of pain to his muscles. But according to the physics, work done is zero. Isn't it? It is creating lot of pain to his muscles in holding this one. All the work he has done in lifting the weight. But when he is hold like this, don't say that you are not doing any work. He may throw that weight on you, isn't it? Okay, fine. See here, how do you interpret the work? Motion of objects again is the applied field. What it is, beta? Motion of the objects. Motion of objects again is the applied field. Okay. So what is the object? Here we are moving under the context of electrostatics. We are moving not mass, we are moving a charge. What is the applied field? Not gravitational field, electric field. I am talking with respect to physics. Okay, beta, fine. So I want to move the charge Q in the presence of the electric field from one point to other point, whatever the path you take. So in order to move a charge from some initial point to final point, I need to do some work. Clear? Yes. So now it is appropriate time to go for a break. It's already 2 hours we have done. Okay. We'll continue after the break. 20 minutes break. Okay, friends, welcome back. Now let us try to understand what is called electrostatic potential. Okay, beta. So we're going to move a charge in the presence of electric field. In order to move a charge in the presence of electric field, one should do work. Clear? Yes. Let us consider a charge distribution here. Charge distribution. When I say charge distribution, it can be a point charge or line charge or surface charge or volume charge or combination of any charges. To make the analysis simple, let us consider the point charge beta. Let us consider the point charge. If you have a point charge, what is there around this one? There is a electric field. So the electric field is E. Units are Newton per Coulomb. Now what I want to do? So there is an electric field is created around this one. I want to move another charge from initial to final point. This is the initial point. Here is the initial to final point. Yes, so in this direction. So if I am here, what is the force on that one? Line joining 2 points. This is the force direction. If I am here, what is the force on that one, beta? Line joining 2 points. Clear? If I am here, what is the force on this one? Line joining 2 points. This is the force beta. If I am here, if I go to near to this one, the force on this one increases. Okay. If I am here, clear beta? Here is a charge Q beta. I am moving a charge Q from initial point to final point. This is initial point beta. And this one is the final point. I am moving a charge from initial point to final point. Clear? And what is the force on that one? We know that the force expression F is equal to Q into E. So if I want to move a charge from this point to this point to this point, I need to move against the applied force, isn't it? Suppose if I am moving from, listen carefully. If I am moving this object from here to here, means what? My applied force must be greater than or equal to the gravitational force. Here also same story. If you want to move a charge from here to here, so externally applied force must be opposite to this one. Then only I can move. Okay, fine. Now I want to find out the work done beta. I'll consider the small piece of length here. Here it is DL. Here it is DL2. Here it is DL3, so on, up to DLN. I'm going to turn the page here. What is the work done by the charge? Work done by the charge. It is by the charge. If you want to move a charge from here to here, my externally applied force must be opposite to the force which is applied by this one. Clear? Yes. So work done by the charge is differential work done is minus F dot DL. Clear? Yes. Why minus? Because externally applied force must be opposite to the applied force. Then only I can move a charge from some initial to final point. Yes. So here it is minus Q into E dot DL beta. So if you want to get the overall work done, what you need to do? Minus initial to final Q into E dot DL. Work done is equal to minus Q initial to final E dot DL. It is a work done. Units are joules. Now what I'll do here, I'll bring this charge here. Work done by the unit charge is equal to minus initial to final E dot DL. Joule per coulomb. This is called potential beta. Work done by the unit charge to bring it from initial to final point. Again is the applied electric field. This is called potential V minus initial to final E dot DL. Units are volts. So what are the units for this voltage V? It is volts. What is this one? Here it is meter. Obviously this E will become volt per meter. So the new units for the electric field is a volt per meter. Okay. So how the electric potential is defined beta? It is the work done by the unit charge to bring it from the initial to final point. Again is the applied electric field. Clear? Yes. Now what is the need for introducing this potential concept? Remember, the potential is a derived quantity. It is a line integral of electric field. The fundamental quantity which exists in the electrical engineering is the electric field. If you have a charge, what is there around that one is the electric field. But intentionally, purposefully, we are introducing the new parameter, derived parameter, what is called a potential. And that too potential is explained with the thought experiment. What is the thought experiment? I am assuming that I am bringing some unit charge from initial to final point. Again is the applied electric field. The reason is very simple. In the electrical engineering, in the circuit theory, the most of the parameter, most of the times you will use what is called a voltage, but not electric field. Isn't it? Why? Because electric field is a vector quantity. If you want to talk in terms of the vector, you need to explain the three components: X component, Y component, Z component. But scalar is the only one component. Just you can say 22 volts, 10 volts, 13 volts, 15 volts, isn't it? So that is the reason why voltage has become very popular than the electric field. Let us try to have some interpretation of this one. I'll going to turn the page. So in the electrical engineering, what you are having what is called a battery. If you have a battery, what is there inside the battery? Due to some electrochemical reaction, isn't it? Battery works on the electrochemical reaction. There is a charge distribution. There is some high charge region, there is some low charge region inside the battery. So what is this battery is giving beta? Battery is giving the charge distribution. Battery is giving what is called a charge distribution. So if you have a charge distribution, what is there around this one? Electric field is there. There is an electric field. So when I draw a single arrow, you must understand that electric field here, 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 everywhere. Okay. If I say that VA is equal to 5 volts, VB is equal to 3 volts. Here it is 0 volts. What does that mean? How can you interpret that one? What is the meaning of that? It is said that what is this one? A potential here is 5 volts. What does that mean? To bring the unit charge from 0 reference point to here. How much work I have done? 5 joules per coulomb. That means 5 joules per coulomb. That means 5 volts. Okay. To bring the charge from 0 reference point to point B, how much work I have done? 3 joules per coulomb. That means 3 volts. Yes. So what is that 0 reference point? First point. 0 reference point, theoretically speaking, the 0 reference point will be at the infinite location. What happens at the infinite point? There won't be any electric field. If there is no electric field at the infinite point, the work done at the infinite point is 0. That is theoretical explanation. Practically, where do you take the 0 reference point? On the earth surface. Grounding. Isn't it? So, from the ground to, from the 0 reference point to bring the charge from here to here, how much work I have done? 5 joules per coulomb. To bring the charge from here to here, how much work I have done? 3 joules per coulomb. That means here I am doing 3 volts work, 3 joules per coulomb, here 5. That means indirectly, what you can say, here I am doing more work. Why? I am doing more work. Why? Because the electric field strength is more there. So if you want to move there to the charge, I need to do more work. So indirectly, what is this 5 volts is saying beta? It is saying that the electric field strength at point A is greater than the electric field strength at point B. Clear? So directly or indirectly, what is this potential is? A potential is the scalar equivalent of electric field. Strictly speaking, what actually existing here is the electric field. But to make the electrical engineering simple, what the engineers have done, engineers have introduced a potential concept so that the potential is a very simple thing. It is a scalar quantity, isn't it? Nowadays, the circuit theory is a basic science. Otherwise, if you are strictly speaking, there will be only electric field. You need to understand all your circuits only with the help of electric field. So this voltage will going to make our life simple. Clear? Yes. You do not talk about all these things in your circuit theory. You just say that you are connected some battery and you have some potential at some particular point as something and other point as other value. Clear, beta? Yes. You do not talk about all these things. You just focus on this one. And there is one more thing which is popular in the circuit theory is a potential difference. What is the potential difference, beta? You'll write it as VAB is nothing but VA minus VB, which is 2 volts. How do you interpret this one? Potential difference. Work done by the unit charge to bring it from here to here is 3 volts. Again, to bring it from here to here is 2 volts. So this is the initial point, beta. This one is the final point. Yes. What is this VA and VB are called absolute potentials. What is this potential difference is giving? It is giving the effectiveness of the electric field between the 2 points. Okay. And what is this VA and VB are called absolute potentials. They are defined with respect to 0 reference point. Here 5 volts is with respect to 0 reference point. Here 3 volts is with respect to 0 reference point. Clear? Yes. So what is the absolute potentials, beta? Potentials defined with respect to 0 reference point. Absolute potential. The potentials defined with respect to 0 reference point are called absolute. Are called absolute potentials. For example, VA comma VB. So for the potential difference, what you need to do? You need to take the absolute potentials. Clear, beta? Yes. Let us have some questions here. And one more thing, you should remember one terminology here. What is that one? Potential at A with respect to B. What is the meaning of VAB? That is potential at A with respect to B. Or VBA, if I write reverse, VBA. This is potential at B with respect to A. Clear? Let us take some questions, beta, here. I'll going to turn the page. And electric field is given by E is equal to 4x x cap plus 2y cap volt per meter. Determine work required to move a unit positive charge along the curve xy is equal to 4 from 2 comma 2 comma 2 2 comma 2 comma 2 to 4 comma 1. Yes, what is the answer, beta? Here it is 2 comma 2 to 4 comma 1. Initial and final points are given in the question. Yes. So what it is? Let us take it as a B. So it is the work done per unit charge. It is nothing but a potential. So this is A is the initial point, B is the final point. Yes. So A, final point potential minus initial point potential. It is V PA. This is initial, this is the final beta. So minus initial point to final point E dot DL. Now you can proceed. You must be careful with this initial and final points as far as potential calculations are concerned. That's all it is. And the rest of the thing is you can handle this one. We have already done the integrations. A to B 4x x cap plus 2y dx x cap plus dy y cap plus dz z cap. 4x into dx plus 2 into dy. Integrate this one. 4 into x square by 2. X limits are from A is the initial point. So here it is 2 to 4 plus 2 into y. Limits are from 2 to 1. Upper limit minus lower limit beta. 2 into 4 square minus 2 square plus 2 into 1 minus 2. 16 minus 2 minus 4, sorry, into 2. It is 24. Minus 2. Minus 22 volts is the answer. Clear? I'm going to turn the page here. Let us take one more question, beta. The electric field. This was asked in the EC paper for 2 marks. The electric field between 2 points A and B is shown. Let psi A and psi B be the electrostatic potentials at A and B respectively. The value of psi B minus psi A is so this is a diagram given. Here it is A, here it is B, here it is 5 micrometers. Here it is 20 kilovolt per centimeter. Here it is 40 kilovolt per centimeter. So the electric field diagram is given. Is asking first us to find out the potential between B and A. What is asking beta? Is asking for psi BA. Why? Because so here it is psi B minus psi A. As I said earlier, I have given interpretation here. This is the initial point. This one is a final point beta. So get the expression for the electric field beta. From there you can proceed. That's all it is. Yes. So I'll consider. Let me give some coordinate system. This is x-axis. This one is y-axis. Clear? What happens to this point? I want to write the expression here. Okay. So what is this point beta? This point is 0, 20 kilovolt per centimeter. This point is 5 micrometers, 40 kilovolt per centimeter. So write down the expression for the electric field. This is the electric field. Write the straight line equation beta. On this axis, we are taking x. On this axis, we are taking the electric field E. So y is equal to E beta. Clear? So find out the electric field expression and then integrate that one. That's all it is. And take the proper limits. So only thing here is you need to know this one. And the rest of the thing is anyhow you know. Integration and all that story. We have spent very qualitative time on the integrals. Vector calculus, isn't it? So what it is? X minus x1. X minus x1 is 0 divided by x2 minus x1, 5 micro. Five into 10 to the power of minus 6 minus 0. is equal to y minus y1. In the place of y, you are having electric field. Minus y1 is 20 into 10 to the power of 3 divided by 10 to the power of minus 2 divided by 40 into 10 to the power of 3 divided by 10 to the power of minus 2 minus 20 into 10 to the power of 3 divided by 10 to the power of minus 2. X divided by 5 into 10 to the power of minus 6 is equal to e minus 20 into 10 to the power of 5 divided by 20 into 10 to the power of 5. Clear, beta? So what is the expression for the electric field? I'm converting into volt per meter. Kilovolt per centimeter is given. I'm going to turn the page here. So what is the electric field expression, beta? E is equal to X. Let me go back. X divided by 5 into 10 to the power of minus 6 into 20 into 10 to the power of 5 plus 20 into 10 to the power of 5. So the electric field expression is X into 4 into 10 to the power of 11 beta plus 20 into 10 to the power of 5 beta. Yes. So what is the potential here? Just it is a scalar. Potential is equal to minus integral of E dot dx. It is one dimensional. What is the initial point? A is the initial point, B is the final point. That means A is the initial, B is the final. That means 0 to 5 micro. Here it is 0 to 5 micro. So here it is minus 4 into 10 to the power of 11 x plus 20 into 10 to the power of 5 into dx. Here it is 4 into 10 to the power of 11 x square by 2 20 into x to the power of 5x. Limits are from 0 to 5 micro. Substitute upper limit minus lower limit. That's all it is. Two into 10 to the power of 11 into 25 into 10 to the power of minus 12 plus 20 into 10 to the power of 5 into 10 to the power of minus 6. So here it is. How much? 50 into 10 to the power of minus 1 plus 100 into 10 to the power of minus 1. Here it is 5 plus 10. Minus 15 volts is the answer. Is that correct? Any algebraic error? Yes. Is it clear, beta? Yes. Okay, beta. Just we have got the expression for electric field from the plot what he has provided. And then what we have done later. And just we have performed what is called integration. That's all it is. There is nothing much about this one. Okay. Let me turn the page here. Let us try to find out the potential due to the point charge, which is very popular question in your exams. Okay. Let us try to get some modified formula. Potential due to point charge, some more theory. Potential due to point charge. Here it is the Q coulombs. Let us consider the point charge beta. What is the electric? If we have a point charge here, what is the electric field? E is equal to Q by 4 pi epsilon r square into r cap. I want to find out the potential here between 2 points. Let us say this is at the location R1 with respect to the origin. This is at the location R2. And I am going from R1 to R2 in this fashion. I want to find out the potential between these 2 points. How do you find out the potential? Potential V is equal to minus initial to final E dot dl. If you have a charge, the electric field is outwards like this, like this, like this, like this from all directions. So the spherical coordinate system we are choosing, isn't it? Yes or not, beta? Okay. Now observe carefully. So here dl is equal to dr r cap plus r d theta theta cap plus r sin theta d phi phi cap. So take the dot product of these two, E into dl beta. So here V is equal to minus initial point is R1, final point is R2. What is this E? Q by 4 pi epsilon r square into r cap. dr into r cap. Okay. So here V is equal to minus Q divided by 4 pi epsilon R1 to R2 1 by r square into dr beta. Okay. So what is the integration of 1 by r square? Actually, small r, capital R both are same. That is the distance it is indicating. Is minus 1 by r. I'll going to turn the page here. So minus is already there. It will become plus. I'll going to turn the page here. So the V is equal to Q divided by 4 pi epsilon 1 by r. Here it is from R1 to R2. V is equal to Q by 4 pi epsilon upper limit minus lower limit. Clear beta? Yes. Now observe here carefully beta. What is this one? This is the initial point. This one is a final point. Very interesting observation. The potential between 2 points is only the function of location of initial and location of final points. Let me go back. Location of initial point and location of final point. But how you are going from the initial to final doesn't matter. Let me call this as a contour C1. Here it is C2. I can go in that way. From initial to final, I can go in this way. Here it is C3. This is initial point. This one is a final point. Clear? Yes. So, what is the observation you have made here? The potential difference between 2 points is only function of location of initial and location of final, but not on the shape of the contour chosen from initial to final. How we are going from initial to final doesn't matter. Yes, let us make that note here. Very interesting observation. The potential between 2 points is only function of location of initial point and location of final point, but not on the shape of the contour chosen. But not on the shape of the contour chosen from initial to final point. Okay, beta? Fine. Now, keep this note aside. While going to talk about that note later. That leads to the very interesting observations in our circuit theory as well. We'll come to this note later again. Remember this note. Now, let us focus on this equation. I want to modify this equation according to my convenience so that I can use that one in solving the questions. I'll going to turn the page here. Let I'll consider, or otherwise let me write down that expression one more time. V is equal to Q by 4 pi epsilon. One divided by R2 minus 1 divided by R1. Let I'll take R2 is equal to R and K is equal to minus Q by 4 pi epsilon R1. So how this will be modified, beta? E is equal to Q by 4 pi epsilon R plus K. What is this K? K is a residue. Residue. What is this K? I'll call it as a residue. Suppose if I want to define what is called absolute potential, For absolute potential, what happens? For absolute potential, absolute potential in the sense R1 tends to 0 beta. R1 tends to infinite, not 0. Absolute potential means what? Potential defined with respect to the 0 reference point. Yes. So if that is the case, what happens to the K1 value? It implies K value is minus Q by 4 pi epsilon R1. This will become 0. And anyhow, we are representing with let R2 is equal to R. So what is the potential? V is equal to Q by 4 pi epsilon R. So I'll give one simple explanation beta here. Simple analogy. Suppose if you are going from Hyderabad to New Delhi. Okay. Hyderabad is the initial point. New Delhi is the final point. But to come to the Hyderabad, already you would have done some work, isn't it? Somewhere here. You have already traveled from here to here. Kanyakumari to Hyderabad. That is a residue. Isn't it? It is a work done at some particular final point from initial point. Final point. Moving from initial to final point, that is the work done. That is the potential. But already to come to that initial point, already you would have done some work. That is a residue. But if you are traveling from Kanyakumari, there won't be any residue. If your initial point is a 0 reference point, then the residue is 0. Clear? Yes. Past work. Okay. You can say like that. Hyderabad, I have taken example. You can take your own example. Because apna, just for example purpose. अपना शेर के ऊपर, शहर के ऊपर प्यार रहना स्वाभाविक है, isn't it? Having the love towards Kushi, okay, whatever it may be, Kushinagar or Gandhinagar, whatever it may be. See, yes, so this is a past work beta. And one more thing here, for the potential difference, what you are taking absolute potentials. To find out the potential difference, you are finding what is called absolute potential. That means this is a potential you need to take for potential difference. This is potential at some particular point. You are traveling from initial point. Again, to come to that initial point, already you would have done some work, past work. That is a residue K. Clear? Yes. Fine. Let me go back here. These two formulas are important. Questions were noticed on these formulas. Now let us focus on this note. After that, we'll go to the numericals. Let us focus on this note beta. What did I say? The potential difference between two points is only the function of location of initial and location of final points. Let me turn the page here. I'll write what is called conservative property of electrostatic field. Conservative property of electrostatic field. Conservative property of electrostatic field. Now let us consider the electric field beta. So when I draw a single arrow, you must notice that the electric field is present in the region. Now what I want to do here, I want to perform the integration, closed line integral. This is point A, this is point B. This is contour C1. This is contour C2. I want to perform what is called closed line integral. Closed line integral of EDL. I can split from A to B EDL plus B to A EDL. This is over the contour C1, this is over the contour C2. From your mathematics, we know that I can just flip the limits and I can put the minus sign there. So what does that mean? Closed line integral of EDL is equal to A to B EDL minus A to B EDL. This is over contour C1, this is over contour C2. So the contour doesn't matter beta. As long as initial and final points are same, the integrals will be same. That is what we have seen, isn't it? So as the contour doesn't matter, so these two values will be same. As these two values are same, what happens? This value will be 0. So the closed line integral of EDL is equal to 0. From the Stokes theorem, what you can write? From the Stokes theorem, closed line integral of EDL is equal to surface integral of del cross E dot dA, which is equal to 0. That happens only when del cross E is equal to 0. Let me turn the page here, beta. So finally, what you have got? You have got a conservative property. What is the conservative property? Closed line integral of EDL is equal to 0. Other one is Del cross E is equal to 0. Yes. So this is in the integral form. This is in the differential form. So always one kind of questions what you can expect in the exam is he'll give the set of options. From there you need to identify the appropriate answer. That I'll classify it as a identification of equations. So you should have a theoretical background of each and every expression you should know. Then you can easily answer that. In the earlier days, that means 5 years ago, there used to be questions like that in the GATE exam. But nowadays it is because of the increased competition. There is no such small questions. But in the engineering service paper, yes, there will be one question on the identification of equations. He'll give some set of options. He'll ask you to identify. The questions will be something like identify which of the following is a Gauss law in the integral form or conservative property of electric field, like this. One question will be there. This is the integral form, beta. This one is differential form. Clear? Yes. Let us have some questions here. And one more thing, before going into the questions, can you guess what is this one? This is one of the popular law in your circuit theory. Come on, speak out what it is. Closed line integral of EDL is equal to 0. That means the voltage in the loop is equal to 0. That means KVL. Very good. Yes. This is a motivation for the KVL. This is not KVL, remember. This is not KVL. This is a motivation for the KVL. KVL is defined for the lumped electrical circuits, isn't it? So the approximation of this one for the lumped electrical circuits will lead to what is called a KVL. Okay, anyhow, we're going to turn the page here. Let us have questions. Find the potential at 4, 1, 0 due to the field E is equal to yx cap plus xy cap with respect to the origin. Options are given. 4 volts, option B. Minus 4 volts, option C 0, option D none. Yes, beta, what is the answer? Minus or plus? Is asking potential. Let me call this point P as a, here is a solution. Four, 1, 0 with respect to the origin. 0, 0, 0. So the potential at point P with respect to origin. That means how you can write potential at point P with respect to origin. That means Vp minus Vo. So this is initial point. This one is a final point. That's all it is. So origin to P, E dot dl, which is equal to minus origin to P, yx cap plus xy cap, dot product with dx x cap plus dy y cap plus dz z cap. Vpo is minus y into dx plus x into dy. Then how can you proceed with this one? How can you proceed with this integral? He has not given any contour in the question, isn't it? But doesn't matter. Whatever the contour you choose, you will get the same answer. That means how you are going from initial to final, he has not specified. You can go like this, like this, like this, like this, isn't it? Anyway. So what is the simplest one? Is a straight line. I'll going to take the straight line better. There is one more mathematical technique. You can directly write this one as d into xy. So here it is xy. X limits, y limits. You can do it like that. Okay. Integral factor. But let me show you in other way. See here, let me talk in something like this. So how we are going from initial to final doesn't matter. So I'll choose the straight path, isn't it? X minus x1, x2 minus x1, y minus y1, y2 minus y1. So y is equal to x by 4. dy is equal to dx by 4. That's all it is. So v po is equal to minus, convert this one into single variable, x by 4 dx. X into dy is dx by 4. Let me turn the page here. One by 2 x into dx. X square by 2. Limits are from, x limits are from 0 to 4. So VPO is equal to minus 4 is the answer. Let us take one more question, beta. Find potential at point A with respect to point B for below charge configuration. Here is a diagram. Here it is 2 nanocoulombs, 1 nanocoulomb. Here it is point A, point B. Here it is 1 meter. Here it is 1 meter. Yes. I'm going to turn the page here. So which formula I should choose better? Potential difference you want. For the potential difference, you need to take the absolute potentials. He's asking potential at A with respect to B. Means what? Here you need to take VA minus VB. What is the formula? Absolute potential? Q by 4 pi epsilon R. So what is the potential at A beta? Is due to two charges. Let me go back. This is 1, this is 1. What about this one beta? This is √2. Clear? I'll going to turn the page here. So what is the potential at A? Is due to this charge and this charge. Two charges. You can use the superposition principle. That is 2 nano. 2 into 10 to the power of minus 9 divided by 4 pi epsilon naught into what is the distance beta? It is 1 meter. Plus, sorry, here it is 1 nano beta. Plus 1 into 10 to the power of minus 9 divided by 4 pi epsilon naught into what is the distance from here to here is √2 beta. And then what is this VB beta? Is due to the two charges. Due to this charge and this charge. Here it is 1 into 10 to the power of minus 9 divided by 4 pi epsilon naught into 1 plus 2 into 10 to the power of minus 9 divided by 4 into epsilon naught into √2. Done? Yes. Now we need VAB. Means what? You need to take the difference of these two. Two into 10 to the power of minus 9. Can I write down directly beta? VAB is nothing but VA minus VB. Take the subtract VAB. What you can take common? 1 by 4 pi epsilon naught you can take common. So here it is. VAB is equal to 1 by 4 pi epsilon naught. 2 into 10 to the power of minus 9 plus 1 by √2 into 10 to the power of minus 9 minus 10 to the power of minus 9 minus 2 into 10 to the power of minus 9 divided by √2. You can take 10 to the power of minus 9 common beta. Ten to the power of minus 9 divided by 4 pi into 1 divided by 36 pi into 10 to the power of 9. So here it is 1 minus 1 by √2. So how much is this? Here it is VAB is equal to 9 into 1 minus 0.707. It is approximately how much? Please check out. .63 volt. Let me turn the page here. We'll take one more question, beta. In the field of a charge q at the origin, the potentials at A 2, 0, 0 and B 1/2, 0, 0 are VA is equal to 15 volts and VB is equal to 30 volts respectively. What will be the potential at C 1, 0, 0? Options are given. This was a previous ES question. Yes, what is answer? Just try this one. I'll be back in seconds. Yes. What is the answer for this? How you got 20 volts? Let me solve this question. There is a charge here at the origin. And there are points. At what point? This is a point B is 1/2, 0, 0. And next point is C 1, 0, 0. Next point is A 2, 0, 0. What is the potential at A? 15 volt. Potential at B 30 volt. Potential at C. Remember, it is not a potential difference. It is a potential. Okay. So you try this one. So at the 2 points, potential is given. At points, not potential difference. I am repeating this point. You need to find out the potential at C. I leave it to this you for your practice. Tomorrow we'll continue. Tomorrow we'll continue with this gradient Poisson's equation method of images. Okay, now the session will be open for your doubts. Yes.
Hello, good evening, sir.
Good evening, Vita.
Sir, in shielding, that is shielding. If we are we are creating means the outside is a positive charge. In the diagram we have shown.
Which example? Shielding
Sir,
example.
shielding.
Mm.
Sir, if we connect any resistor, then there will be a current flow.
No, the charges will be settled. For the current flow to happen,
Because,
there must be some potential.
Because
potential
that resistor is connected to ground and some.
Yes, yes.
Then current will
Yes.
flow or not?
Yes, it will flow.
Then that outside, then how we apply that?
Listen. For the current flow to happen, for the charge movement to happen, there must be some potential difference.
Okay, means that conductor will be have some potential.
Some small, obviously. So this one, as it is charged and it is connected to the ground, obviously some small amount of current will flow.
Okay. Okay. Sir, another.
After that, potential.
Yes, sir. That conservative property of electrostatic field. Here we are getting that electric field only point function. Then it is always valid because we are let's suppose we are writing the KVL equation in a AC circuit. Here also KVL equation valid.
See, as far as we are discussing electrostatics, when it comes to the time varying fields, I'll modify my statement. Modify in the sense, if this flux is enclosed by this one, then this is not valid.
But in case of AC supply also, we are KVL equation that
yes, AC supply also you are doing some. Actually, what happens for the AC supply? Anyhow, I'll going to explain this one in the Maxwell's equations. For the AC supply, this is the thing you will going to get.
And so that part we are neglecting.
This part you will going to get. But as you are dealing in the electrical engineering, 50 hertz, low frequency. So we'll neglect this part.
Okay.
So circuit theory is the approximation of EM theory.
Sir, and in a study book that it takes the convention that work done from A to B is equals to Q into
See,
VB minus.
that is the reason why, to avoid such confusion, I have solved one question. This is a gate question.
Yes.
In the gate exam, this is a convention used. Psi B minus psi A.
Okay, that we are taking. Yes.
This is a gate ECE 2 marks question. And whatever the answer we have got is of minus 15 is the correct answer. It was given by the IIT solution. Okay. What you said is, if that is the case, if you should take this as a final point, this is the initial point, then you would have get plus 15, isn't it?
Yes, right.
This is a gate question. You can even cross check this one in the EC paper.
Okay.
So this is a convention.
Okay, sir. Sir, work done means that is from initial point to final point only.
Final
means,
point.
And if we are going to deal with it, that is potential Q into V final minus V initial. Okay. Okay. Good night.
Yes, Pasha.
Good evening, sir.
Very good.
Sir, in sphere, sir.
Number,
One
page
minute.
number.
After means shielding, after shielding. Sir, in this, if you have any closed surface, then it inside will be 0, sir.
Closed?
Sphere, sorry, closed sphere. If in case we gave as a is condition as a closed sphere, then at the time the inside of that electric field intensity is 0, no?
0. Closed sphere. He has not mentioned that there is a charge inside the closed sphere.
Normally for the sphere inside is non-zero, no, sir.
In the inside the sphere, what is this case? This case, inside the sphere there is a charge.
Yes, sir.
But here,
For this is hollow, open.
hollow. Or here it is a solid one.
Hi, sir. I'm asking in fifth case only for a closed sphere. Sphere is totally closed. At the time, it acts as a hollow.
Hollow. Yes, there should not be any charge. Hollow in the sense that nothing should be there. But here in this case, there is something is there.
If they mention specifically the charge inside, at the time the electric field intensity is
at the time is not equal to 0.
Okay, so it's a mandatory condition for the non-zero electric field intensity. Okay, sir.
If it is a solid one, if it is a hollow one, hollow मतलब खाली है ना बेटा, अंदर कुछ भी नहीं, यहाँ पर चार्ज है.
हाँ, yes sir. मतलब समझ गया मैं fifth case, but I have doubt in if he has a closed sphere, if mentioned as a closed sphere at that time.
Sphere का मतलब है उसका अंदर कोई नहीं, कुछ नहीं है.
हाँ, तो electric field intensity 0 होगी उस time.
हाँ, electric field 0 लेना चाहिए.
Okay sir.
मगर क्वेश्चन में ऐसा मेंशन किया, स्फीयर के अंदर पॉइंट चार्ज है, ऐसा कुछ मेंशन किया तो ये केस होगा.
Okay sir.
So unless and until specified, you have to take it as a hollow or a solid.
Okay.
ठीक है.
Sir, one more sir, in work done, sir. Sir, work done means motion opposite to against the field, no sir. Sir, if you go from the initial to final, at that time that work is okay. If you go from final to initial, it's in the same field, no sir.
Final से initial मतलब वो direction में होगा, कोई work done नहीं होगा ना. So this charge will go into, suppose if I place the final से initial मतलब, so if I place charge there, that will go. It is something like ऑब्जेक्ट को ऐसा ऐसा ऊपर उठाने के लिए वर्क करना पड़ेगा, मगर यहाँ पर छोड़ दिया तो इट विल पिक अप सम एक्सेलरेशन, है ना.
It's access space in.
हाँ.
मींस इन
सेम एनालॉजी, यहाँ पर ऑब्जेक्ट को ऐसा अगेंस्ट द ग्रेविटेशनल फील्ड हटाने के लिए फोर्स करना पड़ेगा, मगर यहाँ से छोड़ दिया तो गिर जाएगा ना।
No return.
यहाँ पर
हाँ,
भी
yes,
ऐसा ही है, वहां पर फाइनल से इनिशियल कोई वर्क नहीं होगा क्योंकि अलॉन्ग द डायरेक्शन है, नो वर्क।
Okay, sir. I got it. Thank you so much.
राइट।
Hello, sir.
यस बेटा।
Sir, 154F.
हाँ,
Sir, here why are we not integrating with respect to F first X and then Y?
फर्स्ट एक्स एंड वाई।
Oh, yes, sir. Means Y dx first Y integrating Y dx and with respect to X and then Y X dy with respect to Y.
No, how can you do integrate that one? That is a variable y. How can you integrate with respect to x? There is a variable x. Here y is there. How can you integrate with x?
Oh, okay, sir.
So I am converting that one into single variable.
Okay, sir.
That's the thing.
Thank you, sir.
Right.
Sir, sir, in this problem where we mentioned this charges being distributed in entire sphere, solid sphere. Sir, my doubt is if you're trying to concentrate any charge, the repulsion force will be extremely high, no, sir?
That is not concentration distributed over the surface. Yes, the forces will be there.
Sir, so in a solid sphere also, if there is a charges that will be distributed on the surface only.
Yes.
So there is no possibility of having any any material that will hold charges. Like you can't basically make a ball of charges.
No. That is the reason why in one of the problem there is an insulating sphere, isn't it?
Yes, sir.
So inside that charges are pumped.
Yes.
We have done one problem, gate question.
Yes, sir. Say pumping charges in the sense like using Van de Graaff or something.
That means inside the insulating sphere, there are charges. Like charges are distributed uniformly in the volume.
Yes, sir.
But there is no, you cannot hold the charges like a ball or sphere of certain radius.
And
if it is a small radius, yes. If it is
sir.
a radius in terms of electrons, 2-3 electrons can stay. All these are physics terminology. Yes. What is the next question?
Next one is choosing this Gaussian surface.
Sir.
So this Gaussian surface we are choosing in order to find out the scalar, that is magnitude of E.
Electric field, yes.
Because direction already we can conclude based on the type of the contour we are taking.
Yes, yes.
For calculation,
that is a prerequisite. You should know the nature of the electric field.
Yes, sir.
Then only you can go with this Gauss law. That is the limitation of the Gauss law. If you do not know the nature, you cannot guess the Gaussian surface, isn't it?
Yes, sir.
If it is a point charge is there, we know that electric field is radially outwards. That is the reason why we have taken Gaussian surface. If that is not the case, we cannot guess.
So you can't approximate it using any other surfaces.
No.
So in that case, how will you solve? So assume some random surface and then use this other theorems.
First one is you need to go back to that integral equations what I have given. These are the standard things. These integrals while discussing the different types of charge distributions.
Yes, sir. That double integral.
Double integral, triple integral. That is how you need to find out the electric field.
Conventional
standard
approach.
Conventional method. That is a standard approach, but unfortunately, what it is the mathematics is tedious. Mathematics is lengthy. That is the reason why, so for some particular uniform charges, see, this is a method used.
Yes, sir.
But mathematics involved is very complicated here. That is the reason why for some type of charges, where you can guess the field, there you can go by the Gaussian surface.
Gaussian method, provided we already know the direction.
You already know the direction.
And sir,
Otherwise-
one more thing I have doubt, sir. It's,
Ah.
regarding this work done only.
Uh,
Right from beginning, like around 11, 12, we have been hearing this work done is independent of the path taken.
that is only for the conservative field. Yes, work done. In the gravitational field is also conservative field.
But only those which are conservative field will have work done being independent of the path.
Yes, yes.
Because whenever I think of any like examples, like you said, this weightlifter thing, it will always contradict me. Like one person is carrying a weight and walking through different parts. Obviously, he may lose energy faster.
That is according to the physics. We are talking only according to the physics.
Yes, sir.
That's all. What your body is spending, how you are spending calories, how much your body is burning fuel. That's what I said. Just to create the interest. Otherwise, I would have said like a force into displacement.
Okay. Sir, one last thing, sir. This notes can get today, sir, uploaded.
Are they not uploaded the last one?
Like I think it was uploaded the next day.
Okay, I'll ask them to do today itself.
All right, sir. Thank you, sir.
Right.
Hello, sir. Hello.
Yes, Mr. Swain.
Sir, that concept is that work done is means here get 2021 also one question came that initial and final point. What is the work done? But in the if the work done is done by the electric field, means that conservative field, it has to be mentioned in the question itself. That what
Obviously,
is the
electric field will be electrostatic field is conservative field.
But sir, when in question it given that what is the work done, means what work to be done by us will be taken care.
Yes.
Okay. Otherwise, it will mention that the what is the field is doing work. Means that will be according
Potential
to
is
negative.
defined work done by the charge only, not on the charge.
But sir, you said na, it is by external force.
By external force, yes, by the charge.
Okay, then it will be negative because Q into E into
Yes.
DL. Then
Yes.
negative. Means
Yes.
we are always calculating minus Q into E into
Yes,
DL.
yes, always that only.
Okay. Means
That is the
never it
production.
will be, never
Never
it
it
will
will be
become.
less. No, no, no.
Okay. Thank you.
Yes, Navdeep.
हेलो सर.
Yes, बेटा.
सर वो 5B 5A वाला क्वेश्चन नहीं है सर.
कौन सा बेटा?
इलेक्ट्रोस्टैटिक पोटेंशियल वाला सर. वो सर उसमें वर्क डन कैसे निकाला, एक बार दोबारा समझाना सर.
ये प्लॉट वाला.
हाँ सर, वो A से B वाला सर.
ये
नहीं, ये वाला सर.
ये
सर.
क्या है इसमें?
ये नहीं सर, इससे पीछे वाला सर.
इसमें पीछे तो ये है
सर
कौन सा है बेटा? विष्णु. नवदीप कौन सा बेटा? अविनाश.
हेलो सर.
हाँ बेटा बोलिए.
हेलो सर.
यस यस.
सर स्लाइड 136.
यस यस.
सर 136.
Yes, it is.
Sir, this case is possible for sphere, sir, but sir, for any other shape, such case can happen, sir.
Either
Sir, any other shapes, suppose, are there an example, then such case can occur, sir, in that also?
Any case can anything can be a question.
Sir, this is for sphere, no, sir. So for other examples where such cases are applicable.
Other examples of the mathematics you can do. If at all, if there is any question, there will be a sphere, there will be a line, and there will be a sheet. If some arbitrary shape is there, how can you do the mathematics for this?
Okay, okay,
That's
sir.
the thing.
All right, sir. Sir, means the fifth number case is only possible for a sphere.
No, other cases also possible. Just I have taken some examples to show you this one.
Okay, okay, sir.
नवदीप बोलिए.
हेलो सर.
हाँ बेटा बोलिए.
सर वो क्वेश्चन सर वो जिसमें इलेक्ट्रोस्टैटिक पोटेंशियल नहीं निकालना सर ए और बी के बीच में सर.
कौन सा पोटेंशियल बेटा? कौन सा क्वेश्चन?
सर
साई बी माइनस साई है क्या?
हाँ सर वो वाला.
ये है यहाँ पर. हाँ यहाँ पर दे दिया ना, देखो अब कहाँ से मूव हो रहा है. ये इनिशियल पॉइंट है.
सर मेरे में लैग कर रहा है सर. ये
हाँ
लैग कर रही है सर. स्क्रीन अभी आई नहीं है वो सर. स्लाइड अभी भी नहीं दिख रहा मेरे में.
नहीं दिख रहा.
नो सर.
स्क्रीन नहीं दिख रहा.
सर लैग कर रही है सर. दूसरा क्वेश्चन दिख रहा है मेरे को अभी.
कौन सा क्वेश्चन?
ये वाला नहीं है सर. इसमें तो -22 वोल्ट वाला नहीं. ये नहीं सर. ये वाला. हाँ ये वाला सर.
ये है. क्या है इसमें दिक्कत?
सर ए टू बी टू ए जाना ना सर हमको सर.
ये टू भी ऐसा दिया क्वेश्चन में दिया. तो मतलब ये होगा इनिशियल पॉइंट, बी होगा फाइनल पॉइंट. वही तो एक्सप्लेन किया था ना मैंने.
सर फिर आप ये वाली इक्वेशन क्यों लिख रहे हो सर? डायरेक्ट ना लिख लेंगे सर यहाँ से. यहाँ
इधर देखो, ये इनिशियल पॉइंट है, ये फाइनल पॉइंट है.
ये सर
डायरेक्ट मतलब यहाँ पर प्लॉट दिया इलेक्ट्रिक फील्ड का. यहाँ पर इलेक्ट्रिक फील्ड का प्लॉट दिया, तो मैंने इलेक्ट्रिक फील्ड का एक्सप्रेशन लेके आया, स्ट्रेट लाइन एक्सप्रेशन इस्तेमाल करके.
अच्छा सर.
ठीक है, इधर देखो, वाई एक्सिस में इलेक्ट्रिक फील्ड लिया और एक्स एक्सिस में एक्स है.
ये सर.
तो डायग्राम दिया, डायग्राम से मैंने इलेक्ट्रिक फील्ड का एक्सप्रेशन लेके आया, उसके बाद उसका इंटीग्रेशन बनाया.
अच्छा सर.
हाँ, दूसरा क्वेश्चन में या ये क्वेश्चन में इलेक्ट्रिक फील्ड डायरेक्टली दे दिया, तो हमने इसका इंटीग्रेशन बनाया. तो यहाँ पर नहीं दिया, यहाँ पर डायग्राम दिया, तो उसका हमने स्केलर एक्सप्रेशन लेके आया, उसके बाद इंटीग्रेशन बनाया.
ठीक है सर.
चलिए बेटा. Okay, I'll going to close the session then. Bye friends. Take care.